Hey guys, I'm going to go over the study guide with you now on projectile motion. The base units for the things that we've covered so far in our MKS units, meters, kilograms, and seconds. Displacement is measured in meters, speed is measured in meters per second, acceleration is measured in meters per second squared, time is measured in seconds, velocity is measured in meters per second, and distance is measured in meters. A ball is thrown straight up at the highest point of its path. Its acceleration is equal to negative 10 or negative 9.8, which we call little g. A ball thrown straight up at its highest point, its velocity is equal to 0. So there's a moment when it changes from going up to down, where it switches direction, where it passes through having a velocity that is equal to 0. A ball is thrown up at 40 meters per second in a situation where there's no air resistance. After 1 second, the velocity of the ball, this acceleration tells you how that velocity is going to change. This tells me that it's going to change by negative 10 meters per second every second. So if it starts at 40, after 1 second, it's going to be going 40 minus 10 or 30. After 2 seconds, it would change by another 10. So it's going to be 30 minus 10 or 20. And then after 3 seconds, it would be 20 minus 10 or 10. A pumpkin is dropped from a 50-meter tall bridge. Assume there is no air resistance. Find the time to hit the ground, the final velocity as, well, it looks like it changed from a pumpkin to a lawn chart while it was falling. We'll change that back to pumpkin. All right, so I'm going to scroll down and clear the ink on this so we have a little bit more room. All right, so this is a one-dimensional problem. We only need to worry about the y direction. So in the y direction, if it's dropped, its initial velocity is 0. Its acceleration will be negative 10. It's always going to be negative 10 unless they tell you that it's not. So it's possible you could be on a different planet or the moon. And the distance that it's falling is 50 meters. We're going to put the displacement as negative 50. So it would start at a location that's 50 meters up and end up at one that's down at 0. And so its displacement would be negative 50 as we take down to be a negative direction. So looking at our kinematics formula, I know that my initial velocity is 0, so that cancels out. So I'm going to multiply both sides by 2. And I'm going to divide both sides by a. And I'm going to square root. And so my time is going to be 2 times negative 50 over negative 10. We need to be careful with the signs that we know what's negative and what isn't negative. If you don't make both of them negative, then your calculator is going to tell you that you have an error. And so I have 2 times negative 50 is negative 100 divided by negative 10 is positive 10. The square root of 10 is 3.16. And then our final velocity, we would just do v equals v naught plus at. So this is going to be 0 plus negative 10 times 3.16, which is negative 31.6 meters per second. And that makes sense, right? So if it's changing by 10 meters per second every second, after 3.16 seconds, it has changed to negative 31.6. All right, I'm going to clear the ink and scroll down a little bit. So that's a one-dimensional problem. So that would be free fall. This one will not be free fall. So we're saying that a piece of paper is dropped from the same 50-meter tall bridge. There is air resistance. It is shaped in such a way that it has constant acceleration, though. So we're allowed to use our equations. A bit of mathematical license with that one. So I want to know what the acceleration is, and I want to know what the final velocity is. So I'm going to say this still starts at 0. I don't know A, but I do know my displacement, and I do know how long it takes. So my displacement's negative 50, and my time is 15 seconds. So I'm looking at the same equation. And now, instead of moving it around to get t, I'm going to move it around to get a. So my initial velocity is still 0, so that goes away. 0 times anything is 0. And now I can multiply by 2. And now we're real used to always dividing by a here. Now I'm going to divide by t squared. And so I get that a is equal to 2 times my displacement over t squared. And so I have 2 times negative 50 meters over 15 seconds squared. And so this ends up being 0.44 meters per second squared. And now again, I'll use my final velocity equals my initial velocity plus acceleration times time to find out what the final velocity is. This is still 0, so I have 0.44 meters per second squared times 15 seconds, and that should have been negative 0.44 meters per second squared. And this is going to give us negative 6.7 meters per second. So this would all be considered a relatively review to the last section. So let's move on to the next section. So I'm going to clear ink and scroll down, and we're going to look at the first type of projectile motion that we looked at, which was horizontal launch. A number of things were special about horizontal launch, and that's why it shows up very often in these problems. Kind of center this a little bit. All right, so during horizontal launch, the initial velocity in the y direction is always equal to 0. So if this is our parabolic flight, we're only looking at the second half of it. And at this point up here, there is no velocity in the y direction. The velocity would all be in the x direction. All right, so number 8, a cart is traveling at 4 meters per second across the table. It falls off the side of the table and falls 2 meters. Find the time it takes to hit the ground, the horizontal distance it travels. So these problems, and the ones that are launched at an angle from level ground, are going to be approached the same way. We have to have 2 charts. So the x direction, the y direction are independent. They're each dealing with their own constant acceleration. In the x direction, that constant acceleration is 0. In the y direction, it's gravity. So I'm going to make an x direction chart, and I'm going to make a y direction chart. And what we're saying is this starts off as 0. So there's no velocity in the y direction to start with. Our acceleration in the y direction is negative 10, and it's going to fall negative 2 meters to the ground. In the x direction, there is no acceleration. So my velocity stays the same throughout. And we looked at this in a number of different instances. In the lab, I showed you some timed photos where you could see that it was traveling the same distance every time. All right, so we're going to use the y direction to get time. We're going to plug it into the x direction. So we're going to do x minus x naught equals v naught t plus 1/2 at squared. I'm going to say that v naught is equal to 0. That's going to go away. I'm going to multiply by 2. I'm going to divide by a. And I'm going to square root. So I end up with 2 times x minus x naught over a to the 1/2 power. So I'm going to plug in my values, and I have 2 times -2 over -10. And so this would be 4 divided by 10, which would be 0.4. And so the square root of 0.4 would be 0.63. All right, now I can look at the x direction because in my chart, these are the same. It's the same problem. So now I can look at what the horizontal distance would be. And now in the x direction, there's no acceleration. So the whole 1/2 at squared goes away. That cancels out. I plug in my velocity, which is 4. I plug in my time, which is 0.63, and I get 2.53 meters. All right, so I'm going to clear the ink and scroll. Feel free to pause the video at any time if you have to, or skip ahead. And we're on to 2-dimensional motion. So what's special about projectile motion is that there is only gravity acting on it. There's no air resistance. There's no other powers, like a rocket powering it. Only gravity is affecting it. The force that we usually ignore is air resistance. So we know that even in the lab there is some air resistance, but we're launching things, even when we went outside, they're going such a short distance and gravity is such a bigger effect on them that we can say that it's negligible. We can disregard it. In projectile motion, the object's path always takes the shape of a parabola. And we just saw this in the first half of this, where we looked at the second half of the parabola. Now we're going to look at the whole parabola. And what's going to happen is, and we see in this question, if a golf ball traveling in projectile motion hit on level ground takes 7 seconds in flight, at what time would it be at its highest point? So it's going to turn out that it's going to be a mirror image, the first half and the second half. So if this is 0 seconds and that's 7 seconds, the highest point is going to happen in the middle. So it's going to be 7 divided by 2, or 3.5 seconds. For the problems we do, they're going to be on level ground. So that means that the displacement in the y direction, my y minus y naught, is going to be 0. Which is beneficial for us because that means that the vertical velocity it heads up with is going to have the same magnitude when it comes down, just opposite direction. All right, so I'm going to clear the ink and scroll down. A golf ball is hit on level ground. It has an initial velocity of 60 meters per second at 37 degrees above the x-axis. Looks like the font changed my degree symbol to something that's not. Assume there's no air resistance. Find the time of flight, the horizontal distance the golf ball travels, and the highest point, the y minus y naught. So before I do a chart, I need to draw my initial velocity, which is going to be 60 meters per second. And that's directed at 37 degrees above. And the idea is that this 60 meters per second doesn't go anywhere in our chart. We want it to go in our charts. We want to find one that goes just in the x direction and one that goes just in the y direction that does exactly the same thing. And so with trig, I can find out what these are. So this side would be my initial and my final velocity in the x direction, and this would be my initial velocity in the y direction. For the x component, I'll use cosine, and I have cosine 37 is the initial velocity in the x direction over 60. So the initial velocity in the x direction is 60 cosine 37. Make sure your calculators are in degrees for these. So I got 48. In the y direction, I'm going to use sine, and sine of 37 is going to be v naught y over 60. So v naught y is going to be 60 sine of 37. And I get 36. So new charts, I'm going to do my x direction and my y direction for my initial velocity, my final velocity, my acceleration, my displacement, and my time. And so those components that we found, the one that goes just sideways is our x direction velocity to start with and to end with. Because in this direction, there is no acceleration. My y direction velocity is the initial velocity 36 positive going up, but when this comes back down, it's going to have the same magnitude. It's going to have the same speed. So this 36 is going to be a negative 36, and I know that I'm on Earth unless they tell me I'm not, and then I'm going from level ground. So I actually have more information than I had for the horizontal launch problems. So now I'm going to use this one to get time, except I'm going to use a different equation because now my V naught's not 0, and I don't want to use the quadratic formula. So I'm going to look at V equals V naught plus AT. And I'm going to subtract V naught to the other side and divide by A. So I'm going to get that T is going to be V minus V naught over A. And so this is going to be negative 36 minus 36 over negative 10. And so that's 7.2 seconds. And I can plug this in to the x direction, and now I can get how far it went in the x direction because, again, my acceleration in the x direction is 0. So this is just going to be 48 meters per second times 7.2 seconds. And I got 345.6. I have 345 there. I'm going to say 346. All right, the other part they ask us is how high is the highest point? Well, what we solve for here is from one end of the parabola to the other. The highest point's going to happen in the middle. So that means that if my total time is 7.2 seconds, the highest point's going to happen at 3.6. So I'm going to do again my x minus x naught equation. And you'll know if you put the wrong time in here because you'll end up with 0 if you put the total time in because you're going to end up back on the ground. All right, so this is going to be our initial velocity in the y direction is 36. Our time is half of 7.2, so this is 3.6 seconds, plus 1/2, be careful with the sign, negative 10 meters per second, and 3.6 seconds squared. And I have I got 64.8 meters. They got 65.6. All right, so I'm going to clear the ink and scroll. And we're almost done with the projectile motion part. And the last part's going to be review of vectors. All right, a golf ball on level ground is on the moon. It has an initial velocity of 50 meters per second at 60 degrees above the x-axis. Assume there is no air resistance. Find the time of flight, the horizontal distance the golf ball travels, and the highest point. So this is going to be the same as the previous problem, but our acceleration is going to be 1/6 as much. So again, I'm going to start with my vector at an angle. They're telling us that this is 60. I'm going to resolve it into its components and solve for what those are. I probably don't need to check to see that my calculator's in degrees still. It should be. And now I'm just going to use trig to solve. So I'm going to say that cosine of 60 is going to be V naught x over 50. V naught x is going to be 50 cosine 60, which is going to be 25 meters per second. And then sine of 60 is going to be V naught y over 50. So V naught y would be 50 sine of 60. Which is 43.3. So when I make my chart, I'm going to plug these in. And so my x direction is 25. My final in the x direction is 25, and this is 0. And in the y direction, this is 43.3. This is negative 43.3. This is, no, look at that. I'm so used to doing Earth, I was going to put negative 10 in there, but they're telling us we're on the moon. So this is going to be negative 1.67. And the displacement's going to be 0. So now I'm going to use this to get the time with my V equals V naught plus AT. I'm going to subtract V naught from both sides. I have V minus V naught equals AT. I'm going to have that T is V minus V naught over A. So I have negative 43.3 minus 43.3 divided by negative 1.67. So we can't just say it's going to be 8.6 seconds because it's not 10. And I got 51.9 seconds. So that goes here, that goes here, and then I can get how far it went in the x direction, which we refer to as the range by using the same original equation. That cancels out, and then I just have 25 meters per second times 51.9 seconds. So I got 1297.5, so 1298. So I'm a little bit different from what that is, but there could be just a little bit of rounding involved. All right, and then they want to get the highest point. The highest point's not going to happen at 51.9. The highest point's going to happen halfway through our parabola. So I'm going to take 51.9 and divide it by 2, and I'm going to round up to 26 seconds. So now I'm going to do my x minus x naught equals v naught t plus 1/2 at squared for 26 seconds. In the y direction, we're at 43.3. Now I gotta remember I'm on the moon. Oh, put a point in there. And we're gonna have 26 seconds squared. And we get 561. All right, so I'm going to clear the ink and I'm going to scroll up and talk a little bit about vectors. So we introduced vectors in this section so that we could work into two-dimensional problems where we were shooting things at an angle. All right, so in order to add vectors graphically, so the tip-to-tail or a head-to-tail method, you have to keep the vector the same length and you can't rotate it at all. So the two things that define what a vector are how long it is, its magnitude, and the direction that it's pointing. So I'm going to take this one and I'm going to put it to the end of that one. And why don't I change this to be black so it looks more like that arrow? So it's pointing to the side. It's about that long. Now that I did, my resultant is going to start at the tail of the first one and end at the head or the tip of the last one. And usually this one is thicker or it is a dashed line, so we know that it's the resultant. So this one does what both of those do. It takes the place of it. I think it might be a little bit better if the light's off. I can't get a good... I haven't made a video in a while. All right, this one here, I have one going down, one going up. I can move either one. I just can't rotate them. I'm going to move this guy over to here. And so I'm going to have an arrow that goes down like that. And then my resultant is going to start where the first one starts and end where the last one ends. So you have to be careful that you're not changing the orientation. You're not changing the length of it. By components is a little bit easier, which we also did that. So two vectors, A and B, have components of -2 and 4 and 1 and 3. What is the magnitude of the resultant? All right, so to add these together, and that's what they ask us down there, what are the components of their resultant? We're going to make a little XY chart. And you're going to have -2 and 4 and 1 and 3. And then we add up those Cartesian coordinates. So I have -2 and 1 is -1. I have 4 and 3 and it's 7. So it's -1 and 7. So they're telling us that this one goes -1. So that's going to be 1 to the left. And then +7. That's going to be 7 up. That's going to be the two sides of my triangle. So it's going this way by 1 and that way by 7. And it's starting here. So it's pointed something like this. And so I can find out how long this is by using a squared plus b squared equals c squared. So c is going to be equal to our 7 squared plus 1 squared, or the square root of 50, which is 7.07. All right, so in this one, they give us 3 vectors that are expressed in Cartesian coordinates. We're supposed to add them together. So I'm going to add the components together. I have 4 plus -2 is +2, plus 6.5 is going to be 8.5. That's my x coordinate. My y coordinate is going to be 3 plus -7, so 3 minus 7 is -4, plus 10 is +6. So in this one's going over 8.5 and up 6. So the arrow would look something like this. They want to know what the magnitude is. That's the side here. So C is going to be equal to the square root of 8.5 squared plus 6 squared, which they're telling us is 10.4. All right, so vectors are going to be things that have direction associated with them. Oh, what is the angle that results that makes the positive x-axis? They're asking us for this angle in here. Because the positive x-axis would just be sideways. I would use tangent. Tan of theta would be equal to the opposite over hypotenuse. I'm sorry, opposite over adjacent. So I have 6 over 8.5. So theta is equal to the tan inverse of 6 over 8.5. Again, make sure you're in degrees, although if you've been working along in this and haven't taken a break, you should have been in degrees the whole time. I know I sound like a broken record over there, but at some point you're going to be in radians in math. So I got 35 degrees, like it said. All right, so scalar or a vector. Distance is a scalar. Velocity is a vector. Speed is a scalar. Displacement is a vector. Mass is a scalar. A man hikes 400 meters south, then 200 meters west, then 100 meters east, then 200 meters north. Let me clear some of this ink and scroll up so we can see this a little better. All right, so I'm going to draw myself a little cardinal directions thing. So I'll take up the smartboard to be north. I'll take down the smartboard to be south. I'll take to the right of the smartboard to be east. I'll take to the left of the smartboard to be west. So I'm going to go 400 south. Then I'm going to go 200 west, so about half of this. Then I'm going to go 100 east, so I'm halfway on there. And then I'm going to go 200 north, so now I'm halfway up here. What is the distance that I hiked? Well, the distance would just be these added together. So 400 plus 200 plus 100 plus 200 would be 900. The displacement would be the distance from there to there. So I know that if I made this into a triangle, this side would be 200 and that side would be 100. Because I went down 400, but I went back up 200. And I went 200 west, but I went 100 back east. And so the length of that would be equal to the square root of 100 squared plus 200 squared, which we're saying is 223.6. All right, what direction is this point in? If I'm just looking at cardinal directions, my arrow is somewhere in here, and so I'm going to say that it is southwest. All right, I'm going to clear my ink. Scroll down a little bit. And again, these are just using trig. So if we're given a vector and an angle, can we find the components, the two vectors that would do the same thing and not change what we have? And so if this is 20 meters at 30, I would have an x and a y. This is 30 degrees. This would be my adjacent side. So I would use cosine to get this. This would be my opposite side. I would use sine to get that. So I would say that cosine of 30 is equal to x over 20. So x is equal to 20 cosine 30, which would be 17.32. And then sine of 30 would be equal to y over 20. So y would be equal to 20 meters sine of 30, or 10. All right, I'm going to clear my ink and scroll. And these are all the same. So I'm going to go through them quickly. We have 45 newtons at 42 degrees. So this side would be 45 cosine of 42. This side would be 45 sine of 42. We have 675 at 1 degree. Jeez. So this would be 675 cosine of 1. This would be 675 sine of 1. We have 123 at 62. So this would be 123 cosine of 62. This would be 123 sine of 62. Number 4, we have 456, almost straight up. So this side down there, I don't have room to write what it is, it's going to be so small, is going to be 456 cosine of 89, and this side would be 456 sine of 89. All right, guys, good luck on your tests, and we'll see you in class.